Hello, everyone. Thank you for listening to my presentation today. My name is Matthew Poncini, and I'll be going over Bayesian networks. Before we get into Bayesian networks, we'll have a quick review of conditional probability. So our rule for conditional probability is that the probability of A and B is equal to the probability of A times the probability of B given A, or vice versa, the probability of B times the probability of A given B. And we can, from that property, we actually get Bayes' theorem, which states that the probability of A given B is equal to the probability of A times the probability of B given A over the probability of B. And so when we have more than two variables, we have an example where there's 4 variables here. We can see that the probability of x1, x2, x3, x4, we can view that as the probability of x1 given the rest times the probability of x2 given the remaining variables, and so forth. And there's the point of the slide is that there's 4 factorial different presentations of calculating this probability. And so that's just something to kind of think about as we take a look at Bayesian networks. All right, so this is more of a generalization. So when there's n many variables, we can describe the probability of each variable occurring as the product of each variable given the previous variables. And so then there's going to be n factorial different ways to describe this product. And then in general, we're going to go ahead and notate parent of xi as the what we are given, the variables that we are assuming have already taken place, or that we assume the value of. Great. So we're going to use a directed graph to describe a Bayesian network. And so each edge is annotated with a quantitative probability. And so there's an example from our textbook. We're given the probability of burglary, a probability of an earthquake, and the probability of an alarm going off is based off of the occurrence of a burglary or an earthquake. And so that gives us this joint distribution graph, and so forth. And so this is what a Bayesian network looks like. The basic properties of a Bayesian network is that each node corresponds to a random variable, which can be discrete or continuous. We are going to look mostly at discrete variables in this project, or in this presentation. And then the directed links or arrows, they are associated with the conditions. And the graph is acyclic. Okay, so each node has associated probability information that quantifies the effect of the parents on that node using a finite number of parameters. So we can go back to our example and we kind of see each of those 3 properties taking place. Okay. So the probability distribution of a set of query variables given a set of evidence variables. So that's what inference in Bayesian networks. It's basically we're trying to figure out what's the probability of Q given the value of variable E. So this is the posterior distribution of Q given the evidence E. And so chapter 13 of the text dives into algorithms that essentially allow us to solve these problems. The first algorithm that's used is enumeration. And so the idea here is that, again, we are trying to find the probability of Q given evidence variables E. And the idea is that we're going to enumerate all hidden variable combinations and then compute joint probabilities and then normalize to get our answer. All right, so here's the algorithm, the pseudocode provided in the text for enumeration. And the easiest way to think about this algorithm is if you're trying to solve this by hand and you go step by step by step. And so we'll be going over this pseudocode with an example. And the example that we're given is the Bayesian network, where we have three random variables. So we have the variable rain, the variable sprinklers, and the grass being wet. So we'll say that there's a 20% chance of there being rain, a 10% chance that the sprinklers went off. And based off of the occurrence of these two variables, we have different probabilities of the grass being wet, right? So if it rained and the sprinklers went off, then we're going to say there's a 99% chance that the grass is wet. If it rained but the sprinklers didn't turn on, then we'll say that there's an 80% chance the grass is wet. And if the sprinklers went off but it didn't rain, we'll say there's a 90% chance the grass is wet. And then if neither of these occurred, then the grass is not wet. Okay, so our algorithm is going to be used to find the probability that it rained given that the grass is wet. So we know that the grass is wet, but we don't know if it rained or if there was a sprinkler or if either of those happened. So we're trying to find the probability that it rained, since all we know is that the grass is wet. Okay. So another way to think of our objective, what's the probability that the random variable R is true, given that our random variable G is true? Okay, so we'll go ahead and start by sort of setting up, connecting our variables to the pseudocode. And so the variable x in this case, that is going to be the probability or the event that it rained. All right. And then our evidence, our observed values for variables is going to be the grass being wet. Okay. So we want to know if it rained, that's x. And we know that the grass is wet. And so that's E. All right. And then when it refers to the BayesNet, that's simply the Bayesian network. And so if we were coding, then we would need to figure out a way to input this information into our code. All right, and again, so we're going to keep in mind that our objective is to find the probability that it rained given that the grass is wet. All right, so we're going to do we'll declare what Q of x is. All right, so Q of x represents the joint probability of essentially the probability that the variable x has its different values. In our case, it's going to be the probability that it rained, and then it could either be true or false. And then given that the evident variable is that we're given, and so that's that the grass is wet, which is true. So we can find Q of R as follows, and then our BayNet variables are simply just the variables that were given in this problem, that it rains, that the sprinklers went off, and that the grass is wet. All right, when we call enumerate, then we're essentially going to need to call enumerate for each value of our x variable. In this case, we'll run it for one time when rain is true, and then run it again when rain is false. So we need to find both of these values. So we'll start with rain being true. All right. We go ahead and jump to our second code, which is enumerate all, and so we will go through these, go through this section of code with the rain variable and the baynet variables. All right, and so our first bars is that it rained, and so we know that since we are assuming we're trying to find the probability that it rained, we're going to say that this is that R is in evidence with the value V. All right, meaning that is part of our problem, so we're going to assume that it's true. And now the probability that it rained being true is 20%. And so now we'll go ahead and set this equal to 0.2 times enumerate all of the remaining variables. All right, so that will push us to enumerate all with S as our variable. S is not in the evidence, so that means that we don't know, we just don't know if the sprinklers went off or not. So what that means is that we need to find we need to kind of cover both cases when we calculate this probability. All right, so that brings us to this else statement. So the probability of E given parents of U, so the probability of S given the parents of S. Well, S doesn't have any parents, so it'll just be the probability of S, and then times the enumeration of the rest of the variables, which is just G. So we have the sum of the products of the probability of the sprinklers going off, which is 0.1, times the enumeration of the remaining variables, plus the probability that it did not rain, or excuse me, that the sprinklers did not go off, times the enumeration of the remaining variables. All right, in our objective function, we're given that the grass is wet, so we're going to say that G is in evidence. And what that means that the probability of grass being true, given that rain's true, given that S is true, is 0.99. And so we can use that. And in our example, we are simply recalling enumerate all each time. But in that first step that we did, we started off with 0.2 times enumerate all, and then each of our follow-up values with the product of each other. And so that's going to give us that'll give us Q of R being true equal to 0.1638. And then we're going to have to do the same process with R being false. Okay, and so if we do the same process, we'll get Q of R being false as 0.072. And then the last step is to normalize. And so we're interested in the probability of rain being true, given that the grass is wet is true. So that'll be our numerator, the true value of Q of R, and then the summation of true or false on the bottom end. And so that will actually leave us with a 0.694 probability that it rained, given that the grass is wet. Okay. And so the enumeration has it is pretty lengthy and arguably inefficient. And so the book presents the variable elimination algorithm, which is a little bit more of a simpler way to do the same exact thing as we did in enumeration. And so we have the pseudocode, and this is a form of dynamic programming. All right. And so the steps, the efficiency lies that they are going to represent local probabilities as factors, and they're going to multiply factors that share variables, and we're eliminating hidden variables one at a time. And then there's going to be a compact expression, which for p of x that we normalize. So same example that we just had, but in fewer steps using variable elimination. And so our factors, we're going to use, notate them as fr of r, fs of s, and then the factor representing the grass being wet, that's going to be based off of the parents, r and s. And so we can view that as the probability of grass given r and s. Okay, so recall that in our objective, we're trying to find the probability that it rained given that the grass is wet. And so our hidden variable here that we're going to eliminate is sprinkler. And so we're going to eliminate that variable. So the way that we eliminate that, according to the variable elimination algorithm, is that we are going to multiply those factors together and find their sum. So we're going to declare that as f prime of r. So a new factor we'll set equal to that dot product. And so we get 0.819. And likewise, so we'll have f prime of r represent that it did rain, and then f prime of not r as that it did not rain. And so we have these two probabilities, which will bring us to step 3, which is to multiply the remaining factors. And so now we only have 2 factors left because we eliminated fs of s because s was hidden, and we eliminated f, g, r, and s because s was hidden there. And so when we want to find qr when r is true, we simply just multiply those 2 factors out. And then when q of it rain being false, we multiply the factors associated with that out. And then we're back to the normalization step, which is what we ended enumeration with. It's the same exact thing. And we get 0.694 again. Okie doke. The Bayesian networks can connect to Markov chains. And so Markov chains are probabilistic graphical models. They evolve from static dependency networks to dynamic sequential models. The main difference between Markov chains and Bayesian networks is that the future state depends only on the current state. And so it doesn't matter. So if we have t as like a temporal variable, that it doesn't really matter what happened 2 iterations ago or 3 iterations ago. It only matters what happened the previous iteration. As far as those are the only thing that changed the probability of the current iteration of x. And then sort of a combination of Bayesian networks and Markov models are dynamic Bayesian networks. And so I leave the slide here as sort of the next steps. This is, I believe, chapter 14 covers a little bit more about Bayesian, dynamic Bayesian networks. But the idea of them is that they handle temporal probability models. And so we have two different products here. The first product handles the temporal transitions, and then the second product handles observations and emissions. And so we essentially, a dynamic Bayesian network, um, it's essentially a Markov chain as well as a Bayesian network. And so there is like a time factor that goes into play, but then we're also going off of observations and evidences, outside of time, outside of like our time restrictions. And so that's sort of like the next piece to Bayesian networks. All right, I'm going to close off the presentation. I realized that every single thing we do in this class, we try to solve two traveling salesmen. Um, I couldn't find a direct way to incorporate Bayesian Bayesian networks into a solution. However, I did think of a more probabilistic approach. And the idea is essentially the algorithm that it came up with is essentially nearest neighbors, except instead of just choosing the nearest neighbor, each neighbor is assigned a weight according to its distance to the current city. And so that weight is defined by a Gaussian equation. And then it's normal, that weight's then normalized to an assigned probability. And so for each current city, as we're building the tour, we start off by creating a random, or just selecting the first city as a random city. And then the next city is selected by probabilistically by the weights assigned to all the remaining cities. And we repeat that process over and over again. And I think that by assigning probabilities, it's very useful. It may not give you, if you just run it one time, you'll get a solution that's not guaranteed better or worse than nearest neighbors. But nearest neighbors doesn't, guarantee you the best results. Just because nearest neighbors prioritizes the beginning of each route as shorter, and then the end of the routes get pretty messy. However, by assigning a probability to each city selection, adding that randomness allows us to run the algorithm a large number of times, and odds are you can keep track of the best of the 10,000 times we ran this code. And so when I did, I used the 40 cities TSP file from Project 3, and then I compared that to the results I got from Project 3. And this approach beat every single one using the closest edge inserts and the closest edge insert variant that I came up with. And so that was pretty promising. However, comparing to Project 4 results, which used the genetic algorithm, the genetic algorithm, the best distance I got with 100 cities far exceeded what I got with the probabilistic Gaussian solution. And so these two values are distant, but it's also, I want to point out that in the genetics algorithm, it was a closed cycle, but in this iteration, it was an open path. So realistically, this has 100 edges in the genetics algorithm, where I have 99 edges in the longer tour. And so this solution is actually much worse. And so future work, I can kind of apply this probabilistic approach to more than just nearest neighbors. And so that'll be kind of interesting to see how that can play out in future solutions to TSP. And then also understanding, you know, why did it work for 40 cities, but then why did it not work so well for 100 cities? Even though I ran it 100,000 times with 100 cities versus only 10,000 times with 40 cities. And so it'll be interesting to kind of play that out and go from there. But yeah, I just had the idea to do more of a probabilistic approach to TSP because, you know, given the city that we currently at, what's the probability that, you know, city A is the next city or city B is the next city? And so presenting that problem this way, I think could be useful in future projects. I hope that you enjoy this presentation. Thank you for listening and take care. Bye.